Welcome to Vector's PREEvision version 9 tutorial series. In this installment, we'll take a short look at the logical architecture layer. So the logical architecture layer is a method to be able to describe your system in an abstract way so that you can visualize the relationship between functionalities and how those functionalities interface with each other. You could say communicate. The logical architecture can be designed completely in the model tree, but it's more often and more conveniently done in a logical architecture diagram. The logical architecture palette includes blocks for logical functions, sense, actuation, service and environment functions, and also something we call a building block. Blocks are connected via ports, and the port type pairs are things like sender-receiver, client-server, controller-slave, environment sender and receivers, or service provided and required. The logical architecture layer in PREEvision, as well as the software layer, work on what we call a type instance approach, so that blocks instantiated from the same type are identical. They have the same behavior, same interface requirements, and they remain in sync with the definition of the type. One example for a use of this concept is functions that differ only by the location of the vehicle. Things like door ajar states, or seat motion, or window position, or tires, or things where there are multiple copies of what are essentially the same thing, but they're just separated by geographic location in the vehicle. This is one note that is going to be relevant in perhaps a future video where we talk about the use of the signal router from the logical layer. Because the type will define the name of the port that is on a logical function, and that name will be the same for all of the instantiations of the type. The receiver is the place where you're probably going to want to have a specific name for the interface so that the router, when it's done creating signals for you, you'll actually have a differentiation between the different locations. I'll go into this more when we go through the router, but this is just a note so that when you're making connections for logical interfaces and ports, that you keep in mind that the name for the signal that's generated by the router is based on the name of the port of the receiver. PREEvision also provides an artifact known as a building block, and that is to allow you to collect sets of functions that will be reused in a coordinated manner. So, for instance, in this case, we've got 4 different window positions, and based on the fact that this is defined as a building block, these 4 functions will always be created and assigned together. It's less going on the diagram, but if you double click on the building block, you'll see actually what's inside of it. So this is a way to try to simplify what's on your diagrams and also to promote reuse of things. So in the logical architecture, ports are connected via interfaces. And the way you define an interface is you actually define it in the library of logical types. And once you've defined a sender receiver or a client server or any of the other types of interfaces that we have, those are then assigned to the ports of the logical architecture by drag and drop operations. Now, again, this is kind of alluding to future videos, but if the software layer is also going to be modeled, so in other words, if you're going to have logical and the software layer both modeled independently, then it's, I would say, typical that the interfaces would be assigned at the software layer and not necessarily at the logical layer. However, If you want to do it in both places, you certainly can. Or if your process does not include using the software layer, then creating and assigning the interfaces at the logical layer is perfectly acceptable and supported. In the logical layer, interfaces have data elements, and those data elements are children of the interface, and they describe the information that's exchanged. Now, this is an example of where we start to get at the logical level a little bit beyond what you would normally expect in a purely abstract way of describing an interface. But if there's no software level definition, if the software layer is not being used, then this is the logical place to do that sort of thing, no pun intended. So in this case, you can see in the tree we've got a logical signal sender-receiver interface. That's just my sort of nomenclature that I apply. And it's probably not a bad idea to develop a nomenclature of your own so that you can understand what you're looking at relatively simply just by these suffixes. And so that logical signal sender-receiver interface has two data elements that are a part of that interface. And then we can continue on from there and define more detail about those data elements to whatever level is appropriate for what we're trying to describe. Again, it's a little bit of a decision that you have to make about how much you want to define at the logical level, and are you planning on going deeper and using the software layer to give more specific details to your data elements and so on. So the next step, and again I'm now alluding to what's going to happen when you want to use the signal router, assuming now that there's no use of a software layer, these logical blocks can be mapped onto a physical network topology. So you can have, for instance, these two logical functions, driver door ajar and passenger door ajar, mapped onto a physical ECU that I just called front ECU in this case. And these two logical functions, called right rear door and left rear door ajar, mapped to a rear ECU. And we also have something called a security ECU that is now mapped to this entry security function, and it happens to be on the other side of the gateway. So when we want to use the signal router to create these signals for us instead of defining them manually, this approach will allow the router to know how these signals have to traverse the connected bus systems. So this is something that I'll cover in more detail in another video, but just to let you know that the reason why we do some of the things that we do at the logical layer is to support future uses of those logical function blocks for the router. Okay, so now that we've talked about some of the concepts in the logical architecture layer, let's create a demo relatively simple logical architecture. So I've created an empty product line with all of the structure below it, and we'll take a look at the logical architecture layer. And this logical function package, you can have as many of these under this heading as you like, this logical architecture layer heading. So you can break this up any way you like. And something that is useful to just do this quickly is you can just double click on this logical function package, and what you'll get is a logical architecture diagram created for you directly. So now we can begin placing our logical blocks on the diagram and connecting them. And usually this is what I find to be the simplest way to approach the development of the logical function layer. So we can start off with just a typical sense function actuation sort of a functional diagram here. So as we mentioned before, whenever there is something used in this layer, it's going to have to be based on a type. So when we're starting from a brand new empty product line, we haven't defined any types yet. But simply placing a logical block on this diagram, we are given the opportunity to define a new block so that we can use that type again later on if we wanted to, or we can just define them one for one, meaning that the type and the instance are essentially the same thing. So in this case, I'm going to create a newly created block, and what I'm going to do is just give that a name, and I'm going to call it door jar. And it has a sender port, and it doesn't have any server ports, it doesn't have any slave ports, and it doesn't have any of these other types of ports. Because it's a sense, it doesn't allow any receive ports to be defined. And we'll see when we get to the logical function, there could have, those logical functions could have provided ports and required ports. But since this is a sense, it's assumed that it's just outputting information. Okay? So when I say OK here, I'll have created a new block type, and the name of the type and the name of the instance are the same. And if I look down in the property view, I can see that the block type is something that I can navigate to directly from this general property page. And when I select that, it sends me to this logical sense type that is actually created as a child of the door jar sense instance that I put on the diagram. Now, if I decided that where I really want this type to exist is in a local library, which I created as a part of the product line, you can just pick that up and move it. So now this type is still the type for this door jar instance, but it's just stored in a library. Tends to make it a little bit easier to organize things if you want to reuse the types. So this door jar block, sense block that we have on our diagram now, I may want to rename this port, but notice that the port prototype is not editable on the property view. That's because it takes its name from the type. So if I want to do anything about the name of this port, I have to do it based upon the type. So if I edit back to the type and change the name of the provided port, I'll see that change in the diagram. In the logical architecture diagram, the names of these ports are based on the type. Another way we can go about creating our types for use in the logical architecture is to just start right in the library and create them in the model tree and then instantiate them later on. So let's say that I wanted to have another new logical sense type. So I can start down in my library, create a new one, and this one I'm going to call it, let's see, window position. And it didn't define any logical sender or receiver ports because that's something that only happens when you're using the dialog that's provided for you when you drag these blocks onto the logical diagram. So I need to create these on my own. So I can just say new logical sender port prototype. And this one, I'll call it window % open. Okay, so now I've got a type with no instances, but I can drag those onto the diagram, and they're instantiated into the diagram just like the DoorJar block is, and the block type is navigable just like what we created by dragging the block onto the diagram originally. It's really up to you what approach you prefer. Both of them work just fine. It's just a matter of what you think is easier. So given that both of these block types are things that really there are multiple copies of, now we can start to look at how these types can be instanced more than one time, and we can make them specific based on changing their names. So let's just say I want to, let's call this vehicle as a coupe, okay? So I've already got one DoorJar instance on the diagram, and I'm going to call this one driver DoorJar. So the type isn't changed, but just the instance name. Now DoorJar state, again, is still going to be just named based on what the type names it, because we can't really do much about the port at the instance level, but we can change the name of the block. So let's say we're going to do a passenger door. So I can take this type, drag it onto the diagram, so I have another instance, except this one I'm going to call passenger door. So still based on the same type, still has the same port name, but the block is named specifically based upon the location in the vehicle. And I can do the same thing with the window position. I'll bring another of those block types into the diagram, and this one I will call it driver window position, and this one I'll call passenger. Now let's create a logical function that can interact with these sense blocks. So I'm going to call this entry control. And I will have, let's say I'm going to have at least one sender, but I know I'm going to have 4 logical receiver port prototypes. And this, I will also have the type end up in the package that we've been using before, which is the local library. And I'll have that go into the logical function types package. Okay, so now I have this entry control function block, and these ports can be moved anywhere on the boundary of the block. Okay, so now I'm going to start connecting these up. So I mentioned in the preliminary description of the layer, that when we're using these port prototype names, they're not going to be specific because they're based on the name of the type, not the instance. But in the case where we've only got one function block and it's the same as the type, the instance and the type are essentially the same thing, I can name these ports to be specific. And then what this will do is, if you eventually plan to run the signal router, the name of the signal will take the name of the logical receiving port. So let's do that right now. So this port prototype we will call driver door ajar state. And we'll just rename all of these. So we've got the two door ajar state ports, and then we're going to need a window %open for each of those as well. Okay, so now we've got all of those ports named the way I'd like them. So if we want to create connections between these, selecting the port and just hovering will bring up this little floating menu so we can create a connection, a logical connection between those ports. And we can do this with all of the rest of these. So at this point, if I was planning on using the software layer, I wouldn't go any deeper into the development of the sender-receiver interfaces or data elements at the logical level. I would tend to want to do that more at the software level. So what we have so far is we've got functional blocks connected via ports. And the names of the ports give you some indication as to what's being communicated over those interfaces, but no additional detail. So this is where I would stop if I was going to start using the software layer to go into those additional details. However, if I am planning on using only the logical level as the input to the signal router, then there are some other things that we have to do. Okay, so the definition of interfaces and data elements begins in the library. So let's go down to our local library and start creating some interface types. So for our sense blocks to our logical function, we're going to use sender-receiver interfaces there. So I'm going to create a new sender-receiver interface, and I'm going to call that door ajar. And I just use the suffix SRI so that I know if I just happen to see that artifact somewhere else what it is. And again, that's just a style thing. That's how I do it, but you can do your own, or you don't need a suffix at all if you don't want it, but I find it helpful. So we can assign this interface to the ports that relate to sender-receiver interface just through a drag and drop. So given that this is based on a type and that sender-receiver interface has been applied to this port, it's automatically assigned to this port because it's based on the type. And because I've already connected these ports via this interface connector, I can see that I've already got the interface assigned. This DoorJar SRI, sender receiver interface, is already assigned to these ports on the entry control function because they've already been connected. If I had just assigned these interfaces ahead of time but never did the connection, this wouldn't have happened. So this is kind of nice. Because of the fact that I've connected them on the diagram, I can assign the sender receiver interface to one end of the connection, and it's automatically assigned to the other. So we can do the same thing for our window position. So we can also create a sender receiver interface for those. And this one I will call window % open SRI. And I will assign that to these ports. And again, the same type of thing happens where I've got this interface assigned to the port, and if I look on the other end of the interface, it's also assigned. Okay, so now that we've created sender receiver interfaces and assigned them to the ports, we can add some data elements to these sender receiver interfaces. So in the case of the DoorJar, we'll do new data element, and that data element, we're going to call it door state, DoorJar state. And I'm also going to put a suffix on this, DE, for data element. So now you should also be able to see right away that this data element is showing up on the interface between these ports. And this one is a little bit difficult to read because they're close together, so it doesn't have a lot of room to put the name. But because we have the same interface definition, sender receiver interface, on both ends of this connection, the data element is shown in the middle. So now let's create a data element for the window % open sender receiver interface. Same process, new data element, and we'll just call that window % open data element. And so the same thing happens in the diagram. It'll end up populating this connector with the name of the data element in the middle, so it's indicating it's the same interface on both ends. So now this data element still has a lot of additional detail that could be defined for it. So on the data element configuration, now we'll start working in the property view. Data element configuration gives you a lot of options about initial values, addressing method, but data type is relatively critical because, again, if we're going to start wanting to use this set of definitions that we're doing right now as input to the signal router, the definition of application data types, implementation data types are going to become relevant. We can also start thinking about Compumethods. A compu method is something that can be applied later on, but can be created somewhat independently. So let's do that now. Let's create a compu method for the Dora jar state. So I'll just go to the package that I created for Compumethods, create a new computation method, and I'll call this Dora jar state CM. Again, I'm using my suffixes as a way to indicate what things are to help me navigate better. Computation method attributes. So there are lots of things that you can define for a compu method: internal to physical conversion, physical to internal conversion, a unit, and these things can be defined directly in the model tree, or you can use this little green plus arrow to create one. So I'll use that method for this version, and so we get a set of different types of internal to physical conversions that we can create. Now, in the case of this Dora jar state, I think I'm just going to create a verbal table conversion. Basically, this is an enumerated variable, or that's the way I want it to end up. So I'm going to choose verbal table conversion, and it's asking me now, where do I want this to be created, the context for it to be created. So I would like it to be in my local library, under computation methods, under Dora jar state computation method. So the result of that is I've got an internal to physical conversion underneath that Dora jar state compu method, and it's called verbal table conversion too, but I would like a little bit more descriptive name. So I'm going to call it Dora jar state table. Now I can start defining the conversion parameters. So the value table at the moment is blank because we haven't created anything. But let's say I'm going to start adding some states here. Now the index is not the same as the value. The value is what's going to go across the network ultimately. The name is what you would expect. It's the semantic meaning of whatever that value will be when it's sent. So I'm going to say that 0 means unknown. The minimum value is 0, the maximum value is 0. That's the same for all of these in the table that I'm going to define. You could, in theory, define a set of discrete semantic meanings that have a min and max that are different as it's transmitted over the bus. But in our case, I'm just going to do this simply. So I'll add another one. This, I will say that the value is closed, and that value is a 1. We'll add another state, and we'll say it's open. So I'll create a state called a jar. Oh, I forgot to fill in the values for these. And let's say we're going to add one more so that we could indicate if our sensing mechanism is failed. Okay, so this is the set of values that I want to be applied to that compu method. So we're done with our definition of the compu method. So now that I've got the computation method defined, I'd like to be able to assign it so that it's referenced by this data element. And the way that's done is through application data types. So we'll use, again, the same create artifact button here, and I'm going to choose an application value type, and we'll give it the context where we want it to end up. I've got a package for application data types, so I'll finish. So it's created one. It's called application value type 3 right now. So I'm going to navigate to that and change the name. So I'm going to call this door ajar state ADT, application data type. So I can set some attributes, and I can also assign a computation method. So the computation method that we just created, I can assign just by drag and drop. So now that data element has an application data type assigned, which also has an assigned computation method. So now let's create an application data type for the window %open data element. Same process, and I'm also going to call this an application value, and I would like this to go into the local library. Where the other application data type went. So this one, again, is generically called application value type 4, and I'm going to change that to window %open ADT. So now we can define a compu method and we'll call this window %open CM. And this, I'm going to define a new internal to physical conversion that I'm going to call a scale linear verbal table conversion. Now the reason I'm choosing that is I want there to be a region of this compu method that is going to convert into a linear value. And I want there to be a part of this compu method that are discrete states. And you'll see with this type of compu method, we can have both of those things in one data. Okay, so we have the internal to physical conversion. I'm going to call this, I'm just giving it an acronym. So the constraints on this, I think I'm going to choose a min of 0 and a max of 255. I'm basically implying by these limits that this is going to be a byte as it's actually implemented. But the compu method really doesn't require a specific size. That happens when we start looking at implementation data types and base types. And we'll get to that. So when I look at the conversion parameters property page, I can see that I've got a linear parameters area and I've got a value tables area. So let's start with the linear parameters. So the minimum is going to be 0. This is where I'm defining my percent. My max is going to be 100. So the min percent and max percent are going to be 100 during the linear range. My factor is 1, my offset is 0. So every bit is multiplied by a factor of 1. So I will have a resulting data area between 0 and 100 that indicates the percentage. Now for the value table section, I'm going to add a state that I'm going to call failed. And that value I'm going to set to 255. So between 0 and 100, that value is representing the actual percent open. If I send to 255, that means that the ability to detect that has been compromised, and that signal is indicating that the provider treats that as a failure of the sensor. Okay. So now that we have defined our compute method, I can go to my application data type and assign the compute method. Okay, so I think I've covered everything that I had planned to in this installment for the logical architecture layer. We've created a simple diagram of a logical architecture where we have some sense blocks connected to a logical function via provided and required ports. We've got the connections between those ports, to which we have assigned sender-receiver interfaces and data elements. We have also defined some Compumethods application data types and assigned those Compumethods to the application data types. So at this stage, if we were ready to look at running the signal router, there are a few more steps we'd have to do, but I think I'll cover that in the next video. Thanks for watching. For more information about Vector and our products, please visit vector.com.